Hello, everyone. We're working through statistical methods for rates and proportions, Chapter 6, Comparative Studies, Cross-Sectional, Naturalistic, or Multinomial Sampling, Section 6.4, Exact Inference for an Odds Ratio Hypothesis Test. So we're going to work with the same example where we're talking about maternal age and the birth weight of the babies. And we're going to read our data set in as we've done in the past. We are going to create a table and we're going to get the joint frequencies of maternal age with the birth weight of babies. So for example, there were 10 people who were in A and in B. Okay, we can get the proportions, the joint proportions by using this prop.table function on T. And by doing that, we get that 5% of the women were in A and B, or 67.5% of women were not in A and not in B. We can use the square brackets to pick off each piece of the proportion table. So for example, the first row, first column will be 0.05, and that would be P11. First row, second column will give us P12, and so on. So we can get all of the proportions and assign them. Then we can get the marginal proportions. That's the P1 dot, P2 dot, P dot 1, and P dot 2. The way we do this is we're going to use the apply function. If we do the apply function on the rows, we get the row sums. And if I just pick off the first element, in this case, I don't have a comma because it's just a vector. Okay. If I choose the first element, that should be 0.25, and the second element, that should be 0.75. Similarly, I can get the column sums, right? And the only thing I change is the second element in the apply function to a 2. The 2 represents columns, the 1 represents rows. So if I look at that, that should be the column sums. And if I pick off the first element, that should be P dot 1, and the second element should be P dot 2. If I want the total of the table, so the number of people in the sample, this is going to be N dot dot. And then I can pick off from T with square brackets the individual frequencies to give me N11, N22, N12, and N21. All right, I can use the apply function in the same way I did before, but now instead of looking at the proportions table, we're just looking at the regular table, and this will give us our marginal frequencies, N1 dot, N2 dot, N dot 1, and N dot 2. Okay, so eventually we want to get the odds ratio. So we're going to start with the probability of B given A, and that is going to be the probability of A and B divided by the probability of A. And then if I want the probability of not B given A, that's going to be the probability of A and not B divided by the probability of A. All right, so when I do this, I get each of those probabilities. And the odds of A is going to be defined by the probability of B given A divided by the probability of not B given A. And these P1 dots, those are going to essentially, when you divide them, equal to 1. So they're going to be non-relevant to get the odds of A, and I'll just get P11 divided by P12, and I get 0.25. Similarly, I can get the odds of not A, and that's by doing the probability of B given not A divided by the probability of not B given not A, or P21 divided by P22. And to get the odds ratio, I'm just going to divide the odds of A divided by the odds of not A. So I will get the odds ratio is 2.25. Now, working through 6.4, we'd like to test a hypothesis, but essentially we are asking ourselves, let's test the hypothesis of the odds ratio, where we assume that the odds are equal to 5 against the two-sided alternative hypothesis where the odds are not equal to 5. All right, we'll need to use the non-central hypergeometric distribution with a total sample size of 200 and the marginals being 50 and 25. Okay, so in this case, we're going to set up a sequence from 0 to 25 by 1. These are all the possible values that x could take on. And there we just assign it from 0 to 25. Okay, we're testing against the null hypothesis that omega equals 5. So we're going to set omega equal to 5. And now I'm going to have to do a lot of calculations, because if you notice, and for equation 6.35, that non-central hypergeometric distribution, the denominator has a summation, right? So I'm going to have to spend a little bit extra work to get that denominator. But it won't be too bad. I'm looking at equation 6.35 in the textbook. Okay, so in the textbook, you can see that the summation in the denominator goes from the max of 0 and the sum of the marginals minus n dot dot up to the minimum of n1 dot and n dot 1. So what I'm doing here is, first I'm creating a list. I called this D list because I was representing the denominator of the list. Okay, the endpoints of the summation, remember in 6.35, are the maximum of 0 and the marginals summed up minus n dot dot, and the top of that summation was the minimum of each of those corresponding marginals. Okay, so for what I'm doing, I'm going to say for these endpoints, right, we're going to get D list, and I use a double bracket here because it's a list. And I'm going to just put what's after that summation sign, right? So it's n1 dot choose I, right, times n2 dot choose n dot 1 minus I times omega to the I. All right, so by using this, I get the summation for the denominator. All right, and if I look at D list itself, it's going to be each of those pieces, right? So it has summed all the way through. And what I'm going to do is I'm going to do the unlist function, and then I'm going to sum. So by doing this, that should give me my entire denominator. Okay, because I want to sum all of those pieces, just like it says in equation 6.35. All right, so when I look at the denominator, here's what the denominator is equal to. It's a very, very large number. All right. Now, the non-central hypergeometric distribution, and I'm using D here, similar to D norm or DF or D binom. Okay, so I'm just calling this the D non-central hyper. And what I'm doing is I'm using the whole equation of 6.35. So the numerator of 6.35, remember, is choose, right? This is how you do choose in R, use the choose function, but it's really n1 dot choose x times n2 dot choose n dot 1 minus x times omega to the x. Okay, so this is giving us the value of the PDF. And remember that I defined x to be 0 to 25. So really, this was not just calculating the PDF at one value of x, it was calculating the PDF at each value of x that I was interested in. So what I can do is I can recreate table 6.4 in our book by putting together x and the D non-central hyper. All right, so that is giving us x in our PDF. And if I look out at this point, this is looking very, very similar to table 6.4. Really, the only difference here is that I don't have the rounded values yet. I'm going to add those in a moment, but as of right now, those values aren't rounded, but they are the same and equivalent to table 6.4 of the text. All right, I'm going to go one extra step and I'm going to calculate the CDF, or the probability that X is less than or equal to some number. Okay, so here we're going to get the p-value, and there's a definition for the p-value in 6.38 in our text, right? And what we're going to do is we're going to look at 6.38 and 6.39, and we're going to say, take the sum of the non-central hypergeometric distribution and do this whenever X is less than or equal to the particular X that we're thinking about. All right, so by running that through, we can actually get all the values in the table, plus we're going to get all the values that are giving us the CDF, right? So in this case, if we look just double spot checking, let's look at 0.16. If we think about this, that's the sum of being less than or equal to 7. So that's 0.13 plus, 0.0013 plus 0.0003, and then all the way up, the rest are almost 0. So then I get a value of 0.0016. So even though these formulas would be somewhat hard to do by hand and somewhat tedious, by using some functions in R, we can calculate these values a lot faster, which is nice. And then we can move on. We can say, let's suppose, right, that we have a value, an observed frequency of 10. So we're asking ourselves, what happens if that 1 cell we observed was 10? What is the probabilities associated with that? So remember, let's look at T itself. And that first cell here, we're saying we observed a value of 10, okay? So if we look at out that we defined earlier, we can get the PDF and we can get the CDF as well. Okay, so the PDF is equal to 0.0335 and the CDF is equal to 0.0535. Okay, so from here we have, right, that the one-sided value is 0.0535. So if we want to know the two-tailed p-value, essentially we can just double that, and that will give us the 0.1070 that they quote in the book. Okay, so from here we are able to get the values based on that particular reference cell. All right, so we can get the two-sided p-value. All right, this is showing us all the PDFs and CDFs. And in our book, it talks about the resulting p-value where we correct for round off. Essentially here, we can look at, let's break this down. We're going to round the table of out where the PDF is less than or equal to the values of out $X equals 10 PDF. So let's look at this. So at 10, right, we have a value of 0.0335. Okay, so now instead of just doubling this 0.0535, what we do is we look at the table and we say, which of these tables have values that are smaller than 0.0335? So here I've pulled up all the numbers into which that has happened. So if I do that, and I actually sum those up, that's how I'm getting the new two-sided p-value. So originally we were just saying, what is the CDF at 10? And we're just doubling that number. Now we're being more intricate and we're saying, okay, if the definition of the p-value is the probability of being as extreme or more extreme than the one in our sample, assuming the null hypothesis is true, what I'm saying is that I know the value at 10 is 0.0335. So now, to be as extreme or more extreme, you need to be smaller than 0.0335. And then I'm only looking at cases that have a value of a PDF that's smaller than that, and then I'm summing them up. That is how I'm getting the resulting two-sided p-value that's corrected for round off. And that gives us the 0.0776. So it takes a little bit more effort to figure that out, but at the end of the day, you get a bit more accurate p-value. All right, I hope you learned something in this section, and I'll see you back in chapter 6, section 6.4, part 2 in a moment.